Welcome back, ladies and gentlemen. This will be a quick one. We're just going to be talking about a position time graph, which is basically the same as a distance time graph, but measuring position instead of distance. This is on page 38 of your booklet. And let's take a look here. So the graph, obviously, being a position time graph, shows position over time. Those are our first two blanks. And it will be measured in meters and seconds most of the time. Could be minutes, could be hours, could be kilometers. It does depend on what we're using. The example that we have on this page is meters and seconds, though, and it's sort of the standard, we'd say. It is a vector type of situation, obviously, because it is position. And the symbol is usually something like this. That's how I mark that it's a position time graph. So, the things we can find, the terms, right? The terms that we can find. First one is the displacement. Okay? And we get the displacement directly off of the y-axis. That's the whole point, right? Displacement is vertical, horizontal will be time. Now the velocity in this case will be the slope. Remember, that's the symbol for slope, a handwritten M. You can just write the word slope, though, if you prefer, in your notes or in the booklet if you've printed it, however you go about doing it. This is exactly the same as what we saw with the distance time graph. The difference is now we're talking about position. So much like before, a flat line means that it's not moving. And a sloped line means constant velocity. And lastly, a curved line means acceleration. That's it. Those are the basic pieces of information. Honestly, I probably should have just done this all in one of the same videos. A position time graph and a distance time graph basically behave the same. There's no real difference between them, with a single exception. A distance time graph will always be positive. Always. Look at the example in our notes right here. A displacement graph or a position time graph does not always have to be positive. I can go up and then I can go down. Why can I go down? Well, because I can go back towards the reference point. See, this would be the position time graph. The distance time graph would look like this. I always get a bigger and bigger distance because I'm always traveling more. It doesn't matter which way I'm going. Because I care about direction, this has positive and negative. But if I don't care about direction, it's just positive. That's it. That's the only difference. So, let's take a look here. We've got some examples that we can fill in. It's going to use this graph here, although actually I guess that graph in our notes is just a little bit different. Goes up, and then it's got like another piece, and then it's flattens out. Something like that. So what are the questions? 1, what information is recorded on the x-axis of the graph? Well, we know that. That's time. We just said that. Time. What unit is the displacement measured? In this one, it's meters. What does this graph show? Position, time, slope. Slope being velocity. How does the slope of the line differ between 4 to 8 versus 24 to 3,000? Well, when we look at that section of the graph, 4 to 8 is about here. So we'll call this A, and here to here is B. And the only difference between A and B is that this one is positive and that one is negative. How many seconds does each line on the x-axis represent? This one is a weird one. So if we look here, we can see that from here to here, is 600. Oops, so I put A in the wrong spot. Silly me. A should be down here. Anyway, so that's 600. And then if I count, there are 5 spaces. 1, 2, 3, 4, 5 spaces from zero start to end. So in order to figure out how much each box represents, I have to take the 600 and I divide it by the 5, and that gives me 120 seconds per line, so 2 minutes. When is the object moving the fastest? From 0 to 240 seconds. Fastest will be 0 to 240. Slowest will be 240 to 1800. And why can we tell that? Well, look at the graph. 240 to 1800, it's got a shallow slope, right? It's very slanted here. It's very almost flat-like. So because it's very shallow, it's barely moving. That's all it's saying. What does the flat section mean? Stopped. We already said that. Okay, so again, remember, we're looking for patterns. If we understand what the patterns mean, everything falls into place very easily. Okay, so let's take a look at the next page here. We're going to look at page 39. This page here talks about calculating the average velocity. So we've actually been doing that already. These notes are just trying to explain in a little bit of detail exactly how we're going to do that. So average velocity, as it says here, the average velocity describes the velocity of an object during any interval of time. Okay, so basically what we're saying is that, shouldn't have erased that graph. So we've got this graph here, right? And it's like this. Something like that. Okay, let's make it a little bit better. There we go. So if I want to know what the average velocity is, that is the velocity during an interval. So I can choose any interval I want. I can choose an interval from here to there. In which case, the velocity is going to be the slope of that line. That part's pretty easy. But what happens if I want, let's do it in red. What happens if I want to find the average velocity from here to there? Oh, well, that's no longer a simple thing. Well, kind of. Because an average velocity is just what speed would I have to do in order to get from here to there if I don't change? Right? The black line represents changing, right? I'm going fast, and then I stop, I don't move for a while, and then I suddenly speed up going the other way. Well, what happens if instead of doing that, I just mosey? I just go slowly at the same speed the entire time. That's what we're looking for here. What is the sort of one single speed that'll get me from here to there? That's why I have that red line that goes from point A to point B. As we can see here, it says in our notes, average velocity describes the velocity of an object during an interval of time, right? So a stretch of time from start to end. So a straight line, now when it comes to these kind of things, we have a special name for this straight line. We call this a chord. Doesn't matter if you really remember that. A chord is drawn between a position at the sort of beginning or initial time and the position that is at the end or final. Now, next part there says the blank, the slope of the chord joining any 2 points on the position time graph will give the average velocity. What does that mean? Okay, well, take a look at the example at the bottom of the page here. It says that a student walking according to the position time graph below, the average velocity for the whole 5 seconds would be found by drawing a chord from start to end. So, if we take that initial one, so let's draw the graph that we've got down there. We're going to work through this one together. You guys have done this before. It's just now we're giving it some names. So we've got ourselves this graph. It looks something like this, and the student goes up, and then they're flat, and then they come back down, okay? So the black line represents what the student is actually doing on this position time graph. But the red line, from start to end, that would be the velocity that I would need to use in order to get from here to here if I just went at the same pace the entire time. In reality, this student sped up, stopped, and then sped up again, right? They changed things around, but they could have just, shuffled along at the same speed, and they would have got there eventually if they had just used this red line. But they decided to run a little faster and then stop for a bit, stuff like that. Okay, so how do we solve this? Well, the velocity equation, if you guys remember, is what we're going to use. So slope, well, what's the slope? What's the equation for the slope of a line? Ooh. Oh yeah, right, we know that one. Slope is equal to delta y over delta x. What does delta mean? Triangle. Change in y. I can change it as y2, y1, x2, x1. Well, in this particular graph, we look at the numbers here, and we can see that this is 0.5 seconds. It's 5 seconds, and it is 6 meters. And of course, he started at 0, 0. So when it comes to filling this in, this one down here is going to be 1. This one is 2. So y2 is 6 over 5 minus 0 over 0. Wow, that one's hard. 6 divided by 5. Well, I'm going to have to figure out what that is. Get out my trusty calculator, maybe. 1.2. So this is the average velocity. You could write it if you wanted with like an AVG right here. That's fine. You don't need to. It's just another way to do it. I could do any average velocity though, okay? So let's try another one. Let's use the blue here. This isn't part of the example anymore, but we're going to do it. Okay, we're going to make something up. So I'm going to choose a point right here, and I'm going to go to there. Okay? So I'm not going from start to end anymore. I'm just choosing 2 random points. Just like this. So I had to look at my graph. Okay, so let's say that that's going to be at 1 second. Right here is 1 second, and it's 5 meters, reading it off the graph. And way up there is 3 seconds at 10 meters. So this one comes first, and this one comes second. So now when I'm going to be filling in my equation, this is the one I did for red. It's the same equation, I just put in different numbers. So the second one is x then y. So x is going to be 3, y is 10, minus 1 and 5. So this is going to be 5 over 2. Get out my trusty calculator again. 5 divided by 2 equals 2.5. I should have known that one. And that will be the average velocity from there, from the blue line, from start to end. And all that represents is that this is the velocity that if I were to travel at that one the entire time, I would get to the same place at the same time as somebody who sped up much faster, but then just sort of like stood there waiting, which is what actually happened. This person really ran and then stood around. Well, instead of running, I could have just walked slowly the whole time. Okay. That's how average velocity works. So you guys can see that on the next several pages here, 42, 43, I believe, you guys can give things a try. 43 is about sketching graphs. Basically, when you draw something without really having any scale. Okay, so much as you saw me do here, right? I didn't write a scale on here. I put the numbers after the fact by checking in the notes. So this is a sketch. A sketch just means a quick drawing to understand things. So see what you guys can do. Page 44 is the start of velocity graphs. We'll talk about those next time. Okay, so keep practicing. Get up to 43. See what you guys can do. Cheers.